Welcome to another video of Optatube. Today, we're going to crack open the super complex, high-stakes puzzle that grid operators are solving literally every single second just to keep our lights on. We're talking about something called Security Constrained Economic Dispatch, or, SCED for short.
See, at its heart, running a power grid is this constant balancing act. On one hand, we all want the lowest possible electricity bills, right? But on the other, the physical grid, it has limits. If you push it too hard, the whole system can just fail. So the big question is, how do you get the cheapest possible power without risking a massive blackout?
Well, that's exactly what we're going to unpack right now. We'll start with the basic problem, then look at the simple goal of just minimizing cost. After that, we'll add the first big rule of grid physics, layer on the all-important safety net, and then, finally, we'll see how it all comes together in a real-world example.
So first up, let's really get our heads around the fundamental problem here, this never-ending battle between keeping costs low and keeping the grid reliable. I mean, think about it. The cheapest power plant might be hundreds of miles away from where you live. Sending all of its power across the grid could be the most economical choice, but what if the transmission lines in between just can't handle that much electricity? That's the central challenge right there.
And you have to understand, the stakes could not be higher. This is not some theoretical problem. Overloading the grid's transmission lines isn't like a simple traffic jam. We're talking about the potential for catastrophic failures, including, widespread blackouts.
Okay, so with that huge challenge in mind, let's build our solution from the ground up. The very first piece of the puzzle is the primary goal of any simple economic dispatch system.
So, before we even start to worry about safety, the system has one simple instruction. Find the combination of power plants that can meet our electricity demand for the absolute minimum cost. In the world of optimization, this is what we call the objective function.
And this is how a computer sees that goal. It's not just a vague idea. It's a very precise mathematical formula, kind of like the one you see here. This equation basically represents the total cost of running all the power plants, and the computer's job is to make the answer to this sum as small as it can possibly be.
But, a cheap price is totally useless if the system isn't physically stable. So, now we need to add our first and totally non-negotiable rule: balance.
This is a fundamental law of physics for the grid. It's not a suggestion. At every single moment, supply has to equal demand, period. If you generate too little, things stop working. If you generate too much, you can actually damage the equipment. It has to be perfectly balanced.
And in math terms, that rule looks like this. The sum of all the power being generated minus the total demand has to equal 0. This is our equality constraint. It's a hard and fast rule that this whole optimization puzzle has to obey no matter what.
All right, so we've got the cheapest cost and we've got balance, but we're still missing the most important piece of the puzzle, the part that actually prevents those blackouts we talked about. This is the grid's safety net. Think of these as the guardrails. Security constraints are simply a set of rules we add to our optimization problem that say, hey, no matter what, you absolutely cannot send more power down a transmission line than it is physically built to handle. A great way to think about this is to compare a transmission line to a highway. A highway can only handle so many cars per hour before you get total gridlock, right? Well, a power line is the exact same way. It has a thermal limit. If you exceed it, you've got a major problem on your hands. So, we add another mathematical rule. Now, this formula on the screen might look a little complicated, but I promise its job is simple. For every single line in the grid, the power flowing through it must be less than or equal to that line's maximum limit. This is our inequality constraint. So you might be wondering, how does the system know how power is going to flow without running a massive, super time-consuming simulation? Well, the secret sauce is something called a power transfer distribution factor, or PTDF. It is an incredibly clever shortcut that tells the model exactly how the flow on any line will change if you generate just 1 more megawatt at a specific spot. It's a game changer.
It's really those PTDFs that make solving this entire puzzle possible in real time. So okay, enough theory. Let's see how all these pieces, the goal of minimum cost, the need for balance, and those crucial safety limits, all come together in a practical example.
We're going to look at a really simple 3-bus system. You can just think of a bus as a specific point or a node on the grid. So we've got 2 power plants, one at bus 1 and one at bus 2. All of our electricity demand is over at bus 3. And crucially, the 3 power lines connecting them all have limits. The system now has to find the cheapest way to serve that demand without overloading any of those lines.
Okay, so after running the optimization, the system finds the perfect balance. It tells the first generator, all right, you're going to produce 83.33 megawatts.
While the second generator is told to produce 66.67 megawatts. Now together, they perfectly meet the total demand.
And the total cost to run the system this way while respecting all of those safety limits comes out to just under 989 euros per hour. That is the single cheapest way to power everything without breaking a single rule.
And this table here gives us the full picture. It shows the exact dispatch for each generator and what it costs. But remember, this isn't just the cheapest solution, it's the cheapest and safest one. The SCED algorithm has successfully balanced the economics with the physics of the grid. Pretty cool, huh?
You know, if you're interested in this kind of stuff, energy market and power system modeling, and you want updates and insights on the global energy market, you should definitely follow the Optatube YouTube channel for more.
So you can see how SCED is really this invisible engine, operating our grid both cheaply and safely every day. And that leaves us with a final thought. We've pretty much figured out how to balance cost and safety with today's resources. But what's the next big challenge for the grid of the future, especially as we start adding more unpredictable renewables like wind and solar into the mix?